Welcome again to my 16th video of engineering thermodynamics, and now for the past two videos we are solving the problems from the concept of first law of thermodynamics, zeroth law and other fundamentals which we have learnt in the first unit, right? Okay, so now we will move to problems and solve some more problems now. So already in the last videos I have explained the three problems which are the topics from fundamental first law of thermodynamics for a process, and how to find out the various energies possessed by the fluid and the control surface which is giving the opposite forces. Okay, now in this problem now what you are viewing here is in a steady flow apparatus. The work done is being given, work done by each kg of fluid. Okay, so here 135 kilojoules of work is positive, and the specific volume of the fluid, pressure and velocity at the inlet has been given, and 32 meter above the floor it meant for, they have given the data for Z, which is used for finding the potential energy. That is, here we have to take into account of the potential energy, and the discharge pipe is at the floor level. So Z equal to Z1 equal to 32 meter and Z2 equal to 0. Discharge conditions has been again given for rho 2, P2 and V2. Total heat lost between inlet and discharges 9 kg per kilogram of fluid is nothing but Q. Last means minus. Okay, it has to be decreased, and in flowing through this apparatus, does the specific internal energy increase or decrease, and by how much? Okay, it is very simple problem, since the data, the surfacious data has been given, and directly if you write the steady flow energy equation with the right unit and substitute means, then you can easily solve the problem. So steady flow energy equation you are writing for the control volume. Here you just can draw, here it is control volume covered by the control surface. Inlet values should be written here, and exit values whatever they have given in the problem, and here Q equal to minus 9 kilojoule. I told you, no, 9 here heat loss between inlet and discharge, so heat loss meant for in the negative sign, or otherwise you can also put the arrow mark which is coming from the system to the surrounding, and then you can write. Okay, so now as I told, first they have written the full form of SFEE. SFEE means steady flow energy equation. U1 plus P1 V1 meant for H1 plus V1 squared by 2 meant for inlet kinetic energy. Z1Z meant for inlet potential energy, plus del Q divided by dm is nothing but per unit mass what is the heat given to the system. Okay, and energies at the outlet. Okay, so now from the arised question, you come to know that you have to find out the difference in internal energy. So you just keep that data to be found in the left hand side, and then bring all the other known data into right hand side. Okay, so here you can substitute all the values, and then why here so many conversions has been taken place, like into 10 power 2 into 10 power 3 is nothing but, if it is in kilojoules you have to match with the unit with other terms if they are in joules. Okay, so that I already have told in my videos which were explained about SFEE. So just the substitutions and the unit conversions. Here del Wx by dm is nothing but 135, and minus del Q by dm only is there, so minus of minus you will get plus. Okay, and finally they have found out that specific internal energy decreases by 20.136 kilojoules. Why they have ends, or they have final resulted with decreases is nothing but here U1 minus U2 they have taken, right? U1 minus U2. So internal energy was um, above the internal energy at the exit, okay, by 20.136 kilojoules. Okay, here if you have made the equation in terms of U2 minus U1, then you would have got the equation, the answer by minus 20.136. So directly you could have seen, but here internal energy difference has been found out like U1 minus U2. It meant for internal energy during the inlet of the fluid was greater than inlet energy at the outlet. Okay, so U1 minus U2 is equal to 20.136. So it is decreasing. Okay. So let me move to next problem. A certain water heater. So here all the problems are under the topic of applications of first law of thermodynamics. So here a certain water heater operates under steady flow conditions, receiving 4.2 kilograms per second of water at temperatures. Enthalpies have been given, and it is heated by mixing it with the steam which is supplied to a heater at the temperature of and enthalpy, that is inlet and exit temperatures have been given, and the mixture leaves the heater as liquid water at temperature 100 degrees Celsius and enthalpies, that is this is for a mixture of both water and steam. Okay, how much steam must be supplied to the heater per hour? Okay, it is like you just think this water heater is the heater which is in your home. Okay, so here inlet is water at the condition of 4.2 kilojoules per second temperature, and enthalpy of the water has been given. And now steam, that is another, in one more side again you are supplying the steam also at the condition of temperature and enthalpy has been given, and the mixture temperature also has been given. Okay, they are now asking how much steam must be supplied to the heater per hour. Okay, so that is they didn't give the mass flow rate of the steam. Okay, but instead they gave the mixtures properties has been given. Okay, so now here by doing the energy balance, first m1 into h1 plus v1 squared by 2 plus z1 g is meant for water plus heat del q by d tau plus this 2, this subscript 2 meant for steam, which is equal to subscript 3 for this energy term consists for mixture and then work done. Okay, so here I hope that you can understand. In heater, what you are expecting? Are you taking any work output? No. So del Wx can be neglected since there is no shaft work. So directly, and other things, velocity, did they give any data related to velocity? No. Z1, Z2, Z3? No. So you can neglect all the terms, and heat supplied has been given, right? Okay, so so here M1 H1 plus M2 H2 is equal to M. Here W1 is nothing but a mass flow rate of water. This is for steam and this is for mixture. So here only thing is this mixture W3 would be the addition of or summation of water and steam, because mass conservation equation tells that M1 plus M2 is equal to M3. Okay, both the mixture of water and the steam would be coming as outlet. Okay, into that enthalpies. Since enthalpies have been given for the mixtures and as well as the ingredients, you can easily write the equation, and then you can find out the mass 2, that is how much amount of steam is required to get the that is required enthalpy. enthalpy of the mixture should be 419. If you want to get that 419 kilojoules per kg of enthalpy, what should be the amount of steam should be supplied? Okay. And now it is very simple for any type of application of steady flow energy equation. What you do is you just write the full form of the SFE and then substitute the data whatever they have given and neglect the unwanted data from the knowledge of what is the purpose of that equipment, so that you can easily arrive the answers. By reading the problem you don't get scared, okay, because if you know the purpose of that particular device, it would be so easy to neglect the terms, okay. And now we will move to third problem. Air at a temperature of 15 degrees Celsius passes through a heat exchanger at a velocity of 30 meter per second, where its temperature is raised to 800 degrees Celsius. It then enters a turbine with the same velocity of 30 meter per second and expands until the temperature falls to 650 degrees Celsius. Now here inlet temperature and velocity, okay, is higher than exit temperature, and velocity remains same, only the temperature is raised for the air. It is entering into the heat exchange. On leaving the turbine, the air is taken at a velocity of 60 meter per second to a nozzle. It is again entered into the nozzle, okay, where it expands until the temperature has fallen to 500 degrees Celsius. If the airflow rate is 2 kilogram per second, calculate the followings. Okay, you have to find out the rate of heat transfer to the air in the heat exchanger, the power output from the turbine, assuming no heat loss, and the velocity at the exit from the nozzle, assuming no heat loss. Take the enthalpy of the air as H is equal to Cp into T, and they have given the values for Cp and T as the temperature. Okay, so here you can see this line diagram of the various equipments present here. Okay, first the fluid is passed through the heat exchanger, and again it is reaching the turbine. From that it is going to a nozzle. Okay, so the purpose of each devices should be known to you. Okay, and the temperatures and other various conditions have been given. Okay, so now from the equation, first thing is, after writing the SFE for eliminating the terms which is not related to other equipments, first you write, if you write for heat exchanger, okay, what they have done is only enthalpy, heat supplied and outlet enthalpy. So here you can able to see, find out the heat supplied in the heat exchanger. Okay, right? So first it is entering into the heat exchanger. So unwanted terms in the SFE could be neglected after writing the SFE, and finally you can find out the heat supplied. Okay, and then again you can write the equation for turbine, and you can find out the work outlet, because the turbine terms would be having this change in enthalpy, velocity, since they have given the velocity, and with respect to finally it was concluded with work done. Okay, and again that third energy equation for nozzle, if you write, only velocity terms and enthalpy terms will come into play, and instead of this H3 H4 directly giving the values, they have given the Cp and the corresponding temperature, so that you can substitute that Cp and the difference in temperature and convert it into joules, so that finally you can get the velocity, the exit velocity. Okay, so now here be clear, first you have to take the data related to heat exchanger, complete it. If you find the outcome of the heat exchanger, then only it is possible to move through the turbine, and again it is going to nozzle, where the purpose of nozzle is to increase the velocity. Okay, so you take this seventh problem, which will be solved in the next video. Thank you for patient listening, and this is Dr. Suja signing off. Meet you in next video. Thank you.